Hi, this is a summarization for the Adversarial Training for Free paper, in which we train robust models efficiently. In supervised machine learning, we train models using labeled data. Let's say we want to build a classifier that can distinguish a panda from a pumpkin. We start off with some images of pandas and also some images of pumpkins. Then usually we have a neural network and we use some optimization routine, such as some variant of stochastic gradient descent, to build this classifier. This classifier works very well on natural images and also images which come from the same distribution as our training data. However, it is known that these classifiers work horribly on adversarial examples. Given a classifier f which maps an image x to the label y, we say an adversarial example x plus delta is something which the classifier incorrectly classifies as something other than y. But we want our adversarial example x plus delta to look like the clean example x, and we can have different measures of this look like property. And one more popular measure is having the perturbation, the delta, which we're going to add to x, be bounded by epsilon in some p norm. The different LP norm perturbation bounds can result in different looking adversarial examples. In this study, we are going to focus on L infinity bounded adversarial examples. Note that adversarial examples can be realistic. Adversarial training is one of the few defenses which has not been broken and is known to make networks robust against adversarial perturbations. Adversarial training involves solving a min-max optimization problem where the maximizer is the adversary which has access to these delta perturbations which are going to be added to the clean image, and the minimizer is the network which has access to the network parameters W. The way that this is practically solved is by training on adversarial examples on the fly. So efficiently what we do is we make adversarial examples, and we, instead of training on natural examples, we train on adversarial examples. And this way we can become robust against adversarial examples. There are many ways that we can generate adversarial examples to train on, and it is known that if we train on weak adversarial examples, we will not be robust against stronger adversarial examples. So we usually do train on adversarial examples made in an iterative fashion, such as the projected gradient descent method. In KPGD adversarial training, we take a mini batch and we have to produce adversarial examples for this mini batch. So what we do is we forward pass this mini batch all the way to the classification layer, and we backward pass that to compute the gradients with respect to the mini batch, and that basically gives us one update on the adversarial examples. And we do this k times. After k times, we have a mini batch of adversarial examples, which is here. And what we do is we basically forward and backward pass this one last time, and this time we do update the network weights. And after this, we go on to the next mini batch. Again, we do k forward and backward passes without updating the network parameters to generate the adversarial perturbations. And then we train on these adversarial examples finally after these k steps. So basically, for every minimization update, now we have an additional k forward and backward steps which we are taking without updating the network parameters. This is why adversarial training has this k factor overhead, where the k is the number of iterations used for generating the adversarial example. While adversarial training small data sets and small networks is feasible, the question is whether it is practical to adversarially train a large data set such as ImageNet. Note that to naturally train a ResNet 50, we need 4 GPUs and 2 days. So if you want to adversarially train the same ResNet 50 on ImageNet data using a 7-step PGD attack, now we need 2 weeks. Whether adversarial training is impractical for ImageNet depends on how many GPUs one research lab has. So adversarial training on ImageNet was done before using hundreds of GPUs and even TPUs. We wanted to make adversarial training doable for labs with small or limited number of compute resources. So that's why we came up with adversarial training for free. In adversarial training for free, we remove the additional k-factor overhead from traditional adversarial training so that our training time is the same as natural training. To do so, every time that we do a backward pass on the network, we use the gradients to update the network parameters. So unlike adversarial training where we have this additional K4 and backward passes where we don't update the network parameters using them, here we update the network parameters every time. So we have this global perturbation which is initialized at 0, and we add that to the first mini batch. So this is the first step of training. And we forward pass and then compute the gradients all the way to the input, and we use all the gradients of the weights to update the weights, and we use the gradient with respect to the input to update this global perturbation. And then in the next minimization iteration, we train on the same mini batch, and we add this perturbation to the same mini batch, and now again we do a forward and backward pass, and we use the gradients of the weights to update the weights, and we use the gradient of the perturbation to update the perturbation. And again we replay the same mini batch for m times. The reason we do so is that if we move on to the next mini batch, the gradients computed for the previous mini batch are no longer that accurate for this current mini batch. After the m replay steps are over, we basically add this perturbation computed on the last replay step of the previous mini batch to the next mini batch. Note that this perturbation is acting as somewhat of a random perturbation. And again, using this next mini batch, we do m replays and m forward and backward passes, and every time we simultaneously update the perturbation and also the network weights. So adversarial training for free is benefiting from the fact that we're updating both the perturbation and the network parameters in one pass simultaneously. And it only has one hyperparameter, this replay, and this replay is somehow simulating the K steps of PGD adversarial training. When we look at our results on the CIFAR 10 benchmark, we can see that compared to the 7-step PGD train model, which is this last row, we can train a lot faster, and we have robustness which is comparable to that. So every column here is referring to a different type of attack, and every row here, except for our last row, is referring to one of our models with a different replay parameter. Note that for the replay parameter 8, we have more robustness compared to the adversarial train model, even though our training time is a lot less, and it is comparable to a natural train model. Adversarial training for free also has additional benefits, which adversarial training had. For example, our free method still maintains the interpretable gradients characteristics of robust models. So, for example, if we look at this cat and we try to basically make this cat into something else for a robust model, if we allow the perturbation to be large, here we're allowing the perturbation to be 50 out of 255, then this cat would turn into this horse, which is not true if we had a naturally trained model. Also, our models have smooth and flattened loss surfaces. If we look at the loss with respect to the input, we can see that compared to a naturally trained model, the robust models, such as our free M models, have very smooth loss surfaces. We use our adversarial training for free algorithm to train different models on ImageNet. Similar to the case for CIFAR 10, we see that we can basically train robust models using different replay parameters. And as we increase the replay parameter, M, our accuracy on natural examples drops. But up to some point, our robustness increases. The good thing about adversarial training for free is that since it's a fast method for training robust models, we can test a lot of hypotheses. For example, we can see that similar to the case which is well known, as we increase the network's capacity, our robustness increases. Our adversarial training for free code is available in both PyTorch and TensorFlow and can be found on our GitHub repos. Thank you very much, and we hope you like this work.